Hello, and welcome to the Intelligent Light webinar, Big Data Challenge, Landing in a Ship Airwake. My name is Shane Wagner. I'll be your host and moderator. It's my pleasure to introduce our presenters, Jim Forsyth and Brad Whitlock. Jim has been a FieldView user for over 15 years. As an active duty Air Force pilot, Jim taught at the Air Force Academy using FieldView in the classroom. His recent work as a member of the Create AV team, coupling a flight simulator with CFD, is what brings us together today. Brad Whitlock is a member of Intelligent Light's Applied Research Group. He is one of the founding developers of Visit, and he will present his work and the role we played helping Jim succeed with his work. So today's agenda. I'm going to give a brief introduction to Intelligent Light and the FieldView family. Then Jim will present on the work he did coupling the flight simulator and the CFD calculations of the ship airwake. Brad will then discuss his role supporting the Kestrel LibSim integration. And then we'll do a Q&A. Intelligent Light has been in business of visualization software and post-processing software and services for over 30 years. With our global customer base, our customers and our connections with the CFD solver world and the hardware manufacturers, we feel that we are a bridge between our customers and the rest of the CFD world. We serve the CFD community with a spectrum of products and services, incorporating visualization, numerical analysis, data management, and automation. FieldView is our primary post-processing software for the desktop and batch operations. The user interface is easy to use, and it's the standard gateway to the rest of our capabilities. Visit, from the U.S. Department of Energy, is an open source solution for scalable post-processing. It is used daily on the largest computing resources in the world. Intelligent Light has used it on in-situ cases running on 100,000 cores. XDBView was introduced last year. It's an open license post-processing and collaboration tool that uses XDBs. XDBs or the extract database technology, provides a compact and portable solution for the big data problem. XDBs form the common core of all of our toolset. And finally, XDBlib is a software library that enables applications such as solver codes and other post-processors to write to the XDB files that will then be read into either FieldView or XDBView. I'd like to pass things over to Jim. Jim, take it away.
All right, thanks. Thanks for having me today. Yes, I'll present the results from a couple flight simulator and CFD using the High Performance Computing Modernization Program, that's HPCMP, Create AV Kestrel. So the HPCMP has a software development effort to create high-performance computing software, and Kestrel is the fixed-wing air vehicles solver. The material I'm taking is from AIAA, this AIAA paper. The co-authors are listed down at the bottom. So Eric Lynch was the other person in NavAir who was responsible for developing the plugin, and Susan Polsky's doing the ship airwake. She's the ship airwake program manager, and Philippe Splart helped with some of the modeling issues that we ran into. So it'll be different from what I present in AIAA because I'll emphasize what we did to integrate Visit into the solver. So outline the talk, give you an overview, then talk about how we implemented it, and then show some results. So the motivation for the project itself was that sea-based aircraft operations have a difficult landing environment. You've got a moving runway, wind over the deck, and complicated structures of the ship cause a significant ship airwake effect that can be very coherent depending on the wind angle and present some challenging conditions for the pilots to land. So they do a lot of flight simulation to train pilots, but traditionally these things, when they want to add the effect of ship air weight, they would just add some random fluctuating quantities into the velocities. But in recent years, they've improved that by doing some CFD calculations of ship air weight, with no aircraft involved, and then saving the data and then using that in a one-way coupling mode to feed that into the flight simulator, just using some sort of linear model for the aircraft and then with the velocities from the air wake. But the problem with that is that neglects any sort of interaction between the ship and the air wake, especially you talk about rotorcraft coming into ground plane effects, but instead of a flat ground plane, you've got a ship. There can be significant interaction effects. So what we proposed to do was two-way coupling of the flight simulator and CFD, in this case of a rotorcraft, and they're moving on to fixed-wing aircraft now. And the goal was then to use these simulations to improve the real-time air wake and ground effect models, because right now we obviously can't do this real-time. That's an eventual goal, but for now it's do the CFD offline. It'll take some time, and then use that to improve the air wake models. That could be also useful for ship design, trying to get a better aerodynamic environment. And like I said, once you get to real-time speeds, you could have a pilot simulation in the loop. So the approach was to couple CASTLE, which is the Navy's manned flight simulation environment, with the CFD solver Kestrel. So CASTLE is the controls analysis simulation test loop environment. And it's kind of a modular environment where you can have all sorts of different aircraft and models that get plugged in. And then Kestrel is a CFD solver, also highly modular, with unstructured meshes near the body, and then the ability to do off-body adaptive Cartesian mesh. For this project, we developed a plugin, and Kestrel allows the ability to create plugins that someone outside the main development effort can do. And we created plugin CASTLE coupler, and that coupled the simulation to the simulator through the rotor. So we would get velocities from the CFD, feed it to the flight simulator, and the flight simulator would give us the locations of the blades. We give it the velocities of those blade locations, and then it would do blade element model and feedback forces on the blades, which we would then put in as a source term into the CFD. We went through kind of a series of cases to test this out: an isolated rotor, hovering, and then a forward flight case, with and without a fuselage, and with the pilot model included, and then finally the ship approach and landing, which is what I'll focus on. So the motivation for doing something like VISIT in this case was that for this simulation, the mesh sizes are on the order of 50 to 100 million cells. You've got several unstructured meshes plus an off-body Cartesian mesh that's adaptive in time. And then we want to do the entire approach and landing, and so the total simulation time is 40 to 45 seconds for that, just the short approach. The other issue was, we're adapting. We have a Cartesian mesh adapting to the rotor weight, and that gives a lot of fine-scale vortical structures, and so you can get a lot of features. And understanding what these features are doing to the actual aircraft and how it's impacting, the pilot model is really important. So we don't want to just do this calculation and look at a bunch of numbers and not understand what's going on. So we really want to see what's going on. But if you want to animate an ISO surface, even if you use 50 frames for a case this big, that can take, an hour, a couple hours. And also, you've got these large files that you have to move back and forth, and that can be challenging to transfer those. And then the fact that all these meshes are moving makes it more challenging as well. So this case, for me, motivated adding extracts to Kestrel, something I'd always wanted to do, but this one kind of seemed to really require it. We looked at a number of options. Helios, which is the traditional rotorcraft create software, uses some other methods, but we decided to go with VISIT for a number of reasons. One, it supports XDB extracts, so we can get stuff into FieldView, which a lot of our users are using. Intelligent Light offered support for integration, so we felt confident that we'd be able to get the support we needed. There are some other options that were completely unsupported this time. The licensing structure enables us to actually distribute Visit and then the library with our solver, so that was a big deal. And it can also support other file formats. So once you get the data that you need, once you get the data into Visit that you need, Visit can then export it as other file formats. Also seem to have good scalability, and a nice benefit is that we get extracts, but then we also, kind of for the same cost, get the ability to do in situ visualization. So look at the sim while it's actually running. So I'll talk next about how we actually implemented this and some kind of issues with that. So if you look at the diagram on the right, this is how you would use Visit completely offline if you just had data files. You'd pull up the GUI, and it could launch multiple compute engines. Each of the compute engines would read a portion of the data spread throughout files. And then when the GUI asks for an isosurface or some sort of visualization plot, the compute engines would get all the data together and send it to the GUI. So on the other hand, this is showing what it looks like if you're running with extracts or in situ, is you actually take your simulation code and instrument it with what's called libsim, and that will then load Visit's engine library as needed when plots are asked for. So that requires a bunch of different routines to be coded that provide callback data. And then libsim will do the communication, handle the communication with the Visit's GUI. When we first started this off, we actually had to launch the GUI in a batch mode without Windows and have it ask for all the plots, ask for the extracts. But version 2.9 had the ability to not even run the GUI. This libsim would do all the would have all the command callbacks you need in order to create extracts and export them. So that has made things a lot easier for us. So the extracts are exported then in XDB format. We made modifications to Kestrel's graphical interface in order to support this. So each extract, you can have multiple copies of it. This is showing a screenshot of it. So the top thing has two isosurface enabled, one that's storing density, isosurface of density, and one that's storing vorticity magnitude. For each of these, you can give it a level, and then you can set the frequency that you want output, and then what output variables you want on those extracts. The way we're doing it, if you ask for an isosurface, you will get that isosurface on all the different meshes that you have. So if you ask for isosurface of vorticity, you'll get one for the Cartesian mesh, for the aircraft, and for the ship. And then you can read those all in individually. So as I said, when you instrument your simulation, each processor then is only going to have a chunk of the mesh. It's going to have its own data. What's nice about that is when you run this in situ, you can actually look at the partitioning, and you know, if you're trying to debug a case and see if there's something wrong going on at processor boundaries, you can actually see that. So this is showing a plot of just a sphere calculation with the colors are the processor number. So for our particular case, when we partition the grid, each processor has a chunk of one of the meshes. For the Cartesian solver, each processor can contain multiple Cartesian blocks. And so this is showing all the different blocks. And so we have to, you know, tell Visit how that's laid out, what blocks are on what processors, and so forth. When you're visualizing this in Visit, you can turn blocks on and off. You can also, for the adaptive mesh, you can turn levels on and off, so you can kind of get some really good debugging information that way. Also, if you identify your ghost cells on your processor, so the cells that aren't being calculated but are needed in order to do the calculations on your compute cells, and then between iterations you synchronize these ghost cells with the compute cells on the other processors. If you pass at these ghost cells, then you can get nice continuous smooth ISO surfaces. And Brad's going to talk about a different way to do it that we used early on. But we didn't at first have these ghost cells available. We only had face-based ghost cells, not the node-based ghost cells that Visit needed. But we have that now, and it's nice because you can actually, if you're trying to debug a case, you can look at what's going on in the ghost cells. One of the other nice benefits for us, especially for debugging, is we have a cell-centered code and for the unstructured solver, and Visit can support that natively. So you can tell it, when you give it your data, you tell it whether it's node-centered or cell-centered, and then pass it the appropriate data. So Visit then, if you want to display it within Visit, then it'll display the variables as being constant within the cell. So you can get a really good, accurate picture of what the computation is actually doing. However, that looks a little funky, so you can also select to view it on nodes, so it'll take the cell center values and interpolate on the nodes for you if you want to view it that way. Okay, but that's all as it's. That's if you're hooking Visit up to look at it. But like I said, when we're doing extracts, we're actually extracting, doing the extracts and dumping them out in XDB format, and then you would look at them in FieldView, which has a nicer interface and easier to use. So, so for results, I'll skip the hover case and stuff like that and go straight to the ship air wake. So this calculation had about close to 9 million cells on the ship, 7 million cells on the helicopter, and these meshes are clipped near the body, and the Cartesian solver then does most of the off-body work. So in this case, the Cartesian mesh started off at actually 30 million compute nodes, and then it grew over time to 50 to 80 million. In this case, we were dumping out a single coordinate plane down the center, and then vorticity ISO that's every 25 iterations. Vorticity ISO surfaces every 10, which is fairly frequent, and then dumping the surfaces out every 20. This was run on a machine Riptide, and we only ran on 320 processors, but the compute time in that case was about 23 seconds per iteration, so relatively reasonable. We were able to kind of do the entire simulation in about 4 days or so. The post-processing from now on that I'll show you is all done using FieldView's GUI, and I did write a Python code that would run FieldView and batch in parallel in order to process the data, because we had quite a few files. That also allowed me, we were running these simulations on the high-performance computing DoD machines, and I was able to create all the plots remotely rather than pulling all the data back. So these ISO surfaces are growing in time because of the adaption, and so to get good scalability, I shuffled up the different time steps before sending it out in parallel to process these. In terms of performance, the Cartesian solver was taking about 63% of the wall clock time, unstructured solver 15%, and creating these extracts was about 5%. That's maybe a little bit higher than when we normally write viz files out, because in this case you're actually doing the calculations to create ISO surfaces, collecting it on a single processor and writing it out. But this was pretty reasonable to have a 5% overhead in this case, and we've made some improvements since then to get even better. And in terms of file size, what you see on the left is the traditional files that we would output, so plot3d files for the coordinates, Q, and then in this case, I was asking for some other variables in the F function file. And then the unstructured meshes for the UH60, and then for the ship and the solution. So you see about just about 2.5 gigabytes for the file size for the traditional full volume. On the right, you see the extract file sizes. The surfaces, ISO surfaces, coordinate planes, much smaller. Obviously, if you ask for a ton of different extracts, then you might get all the way back up to the full solution file size. But if you're asking for a reasonable number of extracts, like we were in this case, the file sizes are 10 to 100 times smaller, depending on what you're looking at. In terms of post-processing time, we ran 2,700 frames, 2,700 samples or iterations. We created that many images and then sewed them back together in a movie. We were looking at ISO surfaces and the surfaces. Doing that with a single FieldView process would take still take a couple hours, 2-3 hours, but farming out in batch, you could get that down to 20 minutes, half an hour. Doing the full volume files would have taken days. So because we were able to do this fairly quickly, we were able to look at, let's do a top view, let's do a side view zoomed in, and get a lot better look at what's going on. And so this is what it looks like. The plot in the lower right-hand corner is looking at the control deflections. So this has a pilot model active. It's trying to pretend like it was a human pilot. So it has some features like that, like a delayed reaction as you would normally get from a pilot. So you've got your collective and your cyclics and your rudder deflections on there. And then this is isosurface of vorticity. And what you'll see from the control deflections is there's a significant amount of motion on the control deflections to kind of counter the air wake. So the way the approach works is the pilot comes in. When he gets lined up, you'll see the rudder pedal kick in, coming up here in a second. You can see the tail wake kind of deflect as he does that. Yeah, right here, he's kicking the rudder pedal in to get lined up, hovers over the deck, and then the model basically waits for it to be in position a certain amount of time to give the landing signal. And then once it's given the clear to land, it'll chop the throttles and then come down. And watch as he comes down. You can see there's a lot of ingestion of wake from the structure in front of him, and I'll show that does have an effect on the landing. So we ran a couple cases. We ran one that just was the flight simulator, how it would normally act. And then we ran the simulation you just saw, and then we ran that exact same simulation, so a two-way coupled simulation, except the ship wasn't there. And so what you're seeing in this right-hand plot is a comparison of the calculation with and without the ship, but with two-way coupling. So if you look at the control deflections, the dashed lines are without the ship, and they're nice and steady. Whereas the solid lines with the ship in there, you're getting the effect of the ship air wake. And then this final phase here is where it chops the throttle, comes into land, and you'll see that first off, with the ship, they land a little bit later. It takes a little longer to get into position and get the clear land signal, and then it winds up landing in about 5 degrees of bank versus the case with no ship. So to show that, what I'll show next is those two cases compared to each other. So the green case is what you've already seen. It's just without the ISO surfaces to get in the way of seeing the aircraft motion. And then the blue helicopter above it is the exact same simulation without a ship, and then I've just translated the blue helicopter up a little bit so you can kind of get a side-by-side look of them. But that's the one that doesn't have any ship in it, but it's still two-way coupled. So this is one that it kind of helps to play through a couple times and look at it. But you can see, how steady the blue ship is without the effect of the ship, and you'll see the other aircraft, the green one with the ship. More oscillations in it. Actually looks more realistic. And you'll notice when it comes down, it lands in a bit of a bank compared to the top one. And you can actually see the flight simulator has a landing gear model. So what you can see when it comes in the lands, that landing gear model showing it's landing on one wheel, then settling down on the other one. And I forgot to mention that besides controlling the rotors, the flight simulator is also doing the 6-stop integration and giving us the Euler angles and positions of the aircraft in time that we're setting in the CFD. So in conclusion, first talk about performance. The file sizes, depending on which files you were talking about, on the order of 10 to 100 times smaller. The transfer times are minutes compared to hours if you want to transfer that back to your desktop. And then post-processing, if you pull this case up and you're looking at it and you want to switch to a different time step, that takes seconds compared to minutes that it would normally take. And then if you want to create a long animation, you can create that in the order of minutes. In this case, maybe it was 60 minutes or 180 minutes, but compared to several hours or days. Batch process. If you batch process in parallel, that can dramatically speed up the process in either case, whether you're doing the full volume files or not. In terms of scalability, I think the performance was reasonable. It was on the order of 5 to 10% of the total simulation time, and like I said, there have been some recent improvement that's gotten that number down further. In terms of memory, the way we implemented it, Visit's got a nice feature where rather than copying data into some data structure to send it, you can pass pointers when possible. So we've done that as much as possible. In some cases, we can't do that, but for all the variable data, that's generated on the fly when Visit asks for it. So if you create only an isosurface of pressure, you'll calculate, you'll hand off a variable for pressure, and then after the iteration's done, and or after you're done doing the extract, and you move on to the next iteration, that memory gets dumped so that it won't clog up the memory. Overall conclusions, having the ability to do these extracts and animations are really valuable, providing some really key insights into what was going on for this particular case, and why was it landing in a bank. There were some differences in rudder pedal deflections between coupled and uncoupled, and we figured that out based on the viz, what was causing that. Also, during this time, we used the in situ ability to do some debugging. We had some issues early on with the Cartesian solver, and we're able to find out that it was a block boundary issue and figure out what was going on in that case. And the in situ capability really helped in that case. And we were able to run in situ, running Visit on our desktop, and then running the simulation on HPC on hundreds of processors and able to connect to it. Getting cell center data is nice to have that handled by default, and we were able to do multiple export options with a simple input change. Basically, you just ask for a different kind of plot and then export it, and you can get what you want. So definitely a big thanks to FieldView for helping out, especially Brad Whitlock, who he's going to talk about some of the fix-ups or some improvements that he did for this project, and he was really helpful answering questions and debugging issues. And just one final animation is showing how the Cartesian meshes adapts in time. This was our forward flight rotor only case, so it does a real nice job of capturing the wake, and it's nice to be able to get these extracts and look at the stuff very quickly. So that's all I have.
All right.
Hand it off to Brad.
Great. Thank you so much, Jim. That was great. And now we're going to pass things over to Brad Whitlock.
Okay, thanks, guys. All right. So I'll be talking about the activities that we did at Intelligent Light to support this integration of LiveSim with Kestrel. And first of all, for those who may not be as accustomed to talking about in situ, we'll just briefly say what it is. So we're running into this situation with research codes and commercial codes alike. They're experiencing this I/O bottleneck. They're generating just massive quantities of data that they can't save because the ability to compute data far outstrips the I/O capacity of the supercomputers that they're on. So what we need to do is move some of our data analysis and visualization that we typically would have done in a post-processing world into the simulation as it's going. So as a result, we can save data that's smaller, more concentrated, more valuable because we've already done some analysis on it. Consequently, since it's smaller, it's going to be faster to post-process it. So we can kind of think of in situ as a way to almost digest the data a little bit so that we can go in after the fact and do some more analysis on it in post. The nice thing about this is a lot of our algorithms that we do for data analysis can be applied at higher frequency when we're running in situ because we're avoiding this I/O bottleneck entirely. We're taking all the time savings that we gained from not doing I/O, applying those to the data analysis, and consequently we're able to do it more frequently. So when we think about what users want, there's sort of a spectrum, but on the left we have one extreme is sort of users want this total automation of data analysis with their tasks. That fits pretty well with in situ because in a lot of cases you've arrived at some kind of analysis that you want to apply to a lot of different runs of your simulations. So using that technique, you're able to generate all these different reports and data extracts and so on. On the far end, what we find is users still want to be able to do the traditional post-analysis with their favorite visualization tool. So a way to accommodate this is by using data extracts. So we've created this in situ workflow whereby we instrument the simulation with Visit and LiveSim, and then that is able to create XDB files, which can then be processed by FieldView. So XDBs are the FieldView extract databases, and of course FieldView natively reads those and consumes them and does so quite efficiently. Now, again, as Jim had said throughout his talk, having applied this workflow to his simulation, he found that the XDBs were easily an order of magnitude smaller than the volume data. And one of the nice things about this in situ workflow is once you get past the instrumentation of your simulation code, the ability to write these XDBs from the solver really enables the customer to go and do post-analysis. And it's not necessarily a Viz expert that has to go and do all this stuff. So the software that we have to enable this in situ workflow, you can kind of think of it as three groups of software that we have cooperating. So first is the simulation. That's passing data through Visit and LiveSim. That's generating XDBs ultimately that are consumed into FieldView. So of course the simulation is just the science code or engineering code that you're instrumenting, generating all the data that you have to be analyzed. And then we're passing that into Visit and then LiveSim. So Visit is an open source visualization and data analysis tool that was started at the Department of Energy at Lawrence Livermore, actually, and has a lot of feature overlap with tools like FieldView. Visit was designed from the start to be run on these HPC systems. The largest run I know of was around 100,000 cores. That was on a Blue Gene Q machine. and we've used it to process data sets in the 8 trillion cell range per time step. LibSim, that's a library that you link to your simulation code to bring visit into the solver's address space to do some data processing. I'll go into how it works in a moment. And lastly, we have FieldView. FieldView is a very successful post-processing tool. There's a lot of licenses worldwide in a range of industries. So when you put all these things together, what you get is the ability to do in situ extracts. So you have your simulation that has LibSim in it. Through LibSim, the simulation is able to expose its data sets, or its data structures, all the different arrays that you want to do post-processing on, except you're going to be doing it in situ. And that gets written out to XDB. XDB is going to FieldView. And again, due to the data reductions that you're able to apply via the extract process, you can perform this far more frequently than you can typically when you are just doing the volume data. So Jim had mentioned that we have support in Visit and LibSim for cell-centered data, node-centered data. I think he also said we had support for adaptive mesh refinement. There are a number of different mesh types that are also supported. So there's the various flavors of structured meshes, rectilinear, curvilinear. Visit also has particle meshes. And then on the unstructured side, there's finite element, zoo elements, and then there are polyhedral meshes that are also supported. And then we have support for different kinds of scalars and vectors that can live on those meshes, and they can range anywhere from 1 to n components. And then there are also support for things like materials and species, which you might find in codes doing chemical reactions. So I'll go into a little bit of how LibSim works now before we go into the section where I'll give more concrete examples about the kinds of features that we added to support Kestrel. But anyway, when you have LibSim, you want to put it into your simulation. You kind of start out, your simulation hasn't been modified yet. So the first thing you need to do is link it with the LibSim front-end library. Now that's a small static library that you can link, and it doesn't really create, add much overhead. Well, it doesn't add any overhead really to your simulation, nor does it increase the size of your executable. Then we have some adapter code that you want to write, and that's the code that you provide to LibSim that it can call as callbacks when data are needed. And that's the code that actually exposes your solver's data structures to Visit in a way that Visit knows to assemble them into meshes and fields and so on. So once you've done your extraction, or your instrumentation of the simulation, this is kind of what it looks like. You've got the original code linked with LibSim, and you've added some adapter stuff to it. When you actually start doing some in situ processing, LibSim loads in the Visit runtime library, and that's a collection of different filtering operations and plotting operations. And they work using this data flow pipeline here. So there's sources and then filters that you can apply. And then in the case of doing data extracts, we throw an export operation at the end. So when this thing actually starts going, you've requested some data, the data from your simulation travels through the adapter, and that gets put as the input to the data flow pipeline in the source. From there, it just starts going from one node of the pipeline to the next, applying the different operations. Finally, at the end, we've gone from the source to the different filters to the export, and in this case, we're writing out to XDBs. So we get the geometry that we need, we write it out to XDB, and then FieldView can post-process that. So in order to support this LibSim and Kestrel integration, we've had to adapt the code a little bit to meet Kestrel's unique needs. So there are basically three things that we had to do to support this integration. One was we needed support for crack-free ISO surfaces using, we didn't have ghost cells initially, so there was another thing that we had to do to expose them. I'll talk about in a moment. And then, since Kestrel has two different meshes, Visit had some long ingrained assumptions about how to deal with meshes, but those assumptions were incorrect. So we had to make some changes to support different parallel meshes with grid to processor mapping. Let's see. Next, we had to add some batch support for LibSim. But anyway, so the bottom line is we worked with Jim through all these issues while he was instrumenting his code. I ended up debugging some issues and making some enhancements to Visit and LibSim and delivering those to the open source version of Visit so they were available to Jim. And those improvements are now a part of the open source version of Visit, and any Visit user is able to benefit from them. So back to the first thing that we did, Visit needed support for, we needed to enable crack-free ISO surfaces in the extracts that we were generating. So Visit has a lot of machinery to support this. Normally it's based on having access to ghost zones or ghost cells in adjacent domains. Now, we initially didn't have that, and it can be quite cumbersome in a code to generate all that stuff, especially if you have to do your own communication from the different processor neighbors. So Visit actually has some machinery to automatically generate ghost cells when needed. It just needs some hints about how to do it. So one of the ways that it can do it is through the use of global node IDs. So we went into LibSim and added support for global node IDs, so you can pass that from the simulation into LibSim, and that gets up to Visit and lets it calculate the ghost cells that it needs to generate these crack-free ISO surfaces. The next enhancement that we did was to address Visit's load balancer. So load balancing, of course, in a parallel application is just a set of heuristics that makes sure that the work in the overall parallel simulation is evenly distributed on the different processors, so you don't have processors taking longer than others if you can help it. So when Visit's load balancer was created, it was assuming that when it saw multiple domain decomposed parallel meshes coming from some kind of data set, that it was assuming they would have the same processor to mesh decomposition, right? So if you look at the picture here, what I'm trying to say is you have a set of NPI processors. Each of them will have a piece of the data, or maybe some of them don't have any data, right? When you do all your computations, ultimately you're going to get, when you put it all together, you get the whole picture. Now, imagine that you had another mesh here on that same set of processors, but it had a different decomposition. So maybe these cells with no data move around a little bit. So if you were assuming that they had the same grid to processor mapping, then when you risk the problem where you ask for data on processors where they don't actually have any data. So anyway, we went into Visit, we enhanced its load balancer so that it would actually get the right grid to processor mapping from the simulation for the mesh that's being requested. And what this means is we no longer ask processors that don't have any data to give us data. So that improved things a lot when we went to use a code like Kestrel, which has these different meshes with processors that, the data might move around on different processors. The final big enhancement that we did was to add a better batch mode to LiveSim. So as Jim said, Visit provides in situ, so you can load up the Visit GUI, and you can connect to your running simulation as though it was just a regular Visit compute server. So you can get the data from the server right into Visit and explore it kind of as it's going. That's great for debugging, and that was actually the use case for which LiveSim was really designed initially. There were a lot of users at Livermore doing really large codes, so they wanted ways to kind of look at the codes as they were going without the need to write data files. So hence LiveSim was born. In the past several years, there's been this push to do purely batch in situ, and that's a response to this I/O problem that I talked about on the first slide. Now, in a batch sense, you obviously don't want any sort of GUI in the picture. You want to run a lot of these solver calculations without much user intervention at all. So the problem that we had with LiveSim and Visit in that case was how to set up the different plots that we want. So it turns out that Visit's viewer up here, which is behind this no GUI sign, this part with the aircraft in it, that's actually Visit's viewer. In Visit, it's the central state manager for how the code asks for things from different components and whatnot. So we needed a lot of pieces of that to put into the Visit runtime, so it could know which plots to set up, which visualizations to create. So we actually spent a fairly intense 6 weeks refactoring Visit's viewer so that we could extract the parts of it that we need to do the state management, and then we incorporated that into the LiveSim runtime library. And that enabled us to create the different plots that we need. So in short, we did a lot of advising initially, and then because of Kestrel's unique requirements, we had to go into LiveSim and Visit, make numerous improvements to it, and those are available in the code now. So anyway, that's all I have, Shane.
Well, thank you very much, Brad.
Sure.
So before we continue, I'd like to remind everybody that you have the ability to ask questions via chat. I'm going to send everybody a chat that says questions. We have had a couple of questions, but please feel free to chat in, and I will ask them on your behalf. So there are some conclusions that bring together the whole project of cooperating with Jim. Jim already gave the conclusions on his project, but one of the things that we're seeing is that it's much easier to make big data, which is creating a different problem. So the bottleneck that Brad described and all the problems that Jim described, and we've been working on a number of different ways to solve that. One of them, of course, is in situ with libsim and XDVs, where you can have extracts that are 10 to 1,000 times smaller than the solution files. And of course, none of this works without partnership. We have all the tools, but really it's working with our partners like Jim that really makes it all work together. So thanks again, Jim. Thanks, Brad. And we'll move on to the Q&A. A couple of questions here. First one is for you, Jim.
So how do you create boundary surface extracts in Visit? So,
No, that one.
Visit doesn't really have the notion of kind of like define your mesh and then tag things as boundaries. So what you do is you create another mesh that is just your boundary surfaces. So in my case, this case was a 3D case, so you define what your topological dimension is, I think is what it's called, something like that. So I'd say that it's a two-dimensional mesh. I mean, it's a 3D mesh, but with a 2D topology, and then get all my surface faces, and you still call them cells, but that's essentially what you do is you just take all your surface faces, create a mesh based on that. So when I'm plotting this in Visit, you'll have you'll have your volume mesh, and then you'll have a surface mesh that's separate. And then to kind of tag boundary conditions, Brad recommended that what I do is kind of label each different boundary surface with a different material property. And so I use the material properties I give it are the boundary condition name.
And Brad, did you want to add anything to that? That was really more a question for you, right?
That's perfectly fine. I would like to add to it, we have been working on a way to natively represent boundary surfaces within Visit. So that's in kind of a research branch of the code right now. And so we'll have a more natural representation than using materials in future versions of Visit. We're still working on some of the issues, but we've got some good stuff working at this point.
Okay. Brad, there was another question, which was, how long did it take you to get the libsim stuff working with Kestrel for this project?
Well, so I actually didn't do the libsim integration with Kestrel. That was all Jim. So I guess maybe a testament to this is stuff that people who are familiar with the solvers can add themselves. But Jim, why don't you field that?
Yeah, initially, I don't know, maybe kind of a month, but we ran into a lot of issues that you had to deal with, like the fact that I have a Cartesian mesh that goes on all processors, and then we have multiple MPI groups with each unstructured mesh on a different MPI group, and that caused some issues, and then ran into the ghost node issues. One of the things I spent a lot of time on was the Brad helped out with was how do I launch Visit in batch, at the same time I'm executing my code, and then have messages passed to the Visit GUI, with no windows in order to get the extracts. That's become tremendously easier with 2.9 and having libsim actually do all that work so that you don't have to do that. So it took me a while, I think. If I went back and did it now with the state of the code as it is, it would be a whole lot quicker.
I'd also comment, I think compared to a lot of codes, Kestrel has a lot of features to support in a proper integration. So
okay.
I would say its difficulty level would be higher than a lot of codes.
Okay. Jim, a question about Kestrel. Do you have some other examples of the types of projects that Kestrel's been used for or can be used for?
It's got a number of capabilities. It has a full finite element solver Sierra inside it, so you can do full structure analysis coupled to the CFD. It's also got a linear modal structural solver. Don't do chemistry. It's got, like I said, the unstructured solver near the body, Cartesian adaptive mesh off body. And yeah, those are kind of the big features. I know I'm missing some. Oh yeah, you can also do solving in a rotating reference frame. So if you want to do like a rotorcraft and hover, you can solve that at a rotating reference frame to get faster convergence. Also, of course, it does all sorts of motion. And it has a 6DOF module to do 6 degrees of freedom calculations, including some constraints like rail constraints, ball joints, hinges, and control surfaces. You can define control surfaces using mesh deformation, or you can do it with overset as well, and obviously has overset. And then with the so you can do control surfaces using overset, or with where you have like a plane that you define where you have a sliding interface, and then you deform your flap up and down within that sliding interface. And also you can have like a region embedded in another region with the whole interface between the two sliding, and it does conservative interpolation between the two. And also has engine, you can integrate engine models. So there's a number of engines that have been coded up as engine models that you can, if you have a source sink boundary condition, instead of just crudely putting stuff in, you can actually put it in as engine inlet, engine outlet, and have the engine module calculate what happens in between and set the boundary conditions. And then you can control like the power level angle for the engines.
Okay. All right. Well, of course, we have now instrumented visit with Kestrel. There came a question about other codes that we've done, and I know that we've done it for the NASA Fund 3D and overflow code, as well as Georgia Tech ABT Leslie. Brad, as far as I understand, there's a question here about is there a list of codes that we can integrate to? I think the answer is any code, right?
Yeah, I mean the answer is any code. Is there a list of codes that we have integrated with? I don't actually. I haven't gone to compile that list. I mean, there's several that I know of from various national labs. Like AL3D is a good one from Lawrence Livermore. I'll be honest. I find actually that people tend to pick this up and go instrument their codes, and I don't tend to know about it until they submit a paper or something.
Right.
So.
Okay. All right. So we'll be on the line for a couple more minutes. If there are any more questions, please do use the chat feature. Again, I want to say thanks to everybody for joining us. Thanks to Jim. Thanks to Brad. All right. Well, we've come to the end of the 1-hour session. Thanks again, everybody. We'll hang on the line for just another minute or two, but that seems to be all the questions we've had. So we'll say goodbye, and thanks very much.